Hello, this is Richard Hammack's Calculus 1. We are in part 2 of the course on limits. Today, lecture 11, continuity and limits of compositions. We'll define a very important issue called continuity. The deeper you go into calculus, the more and more important continuity becomes. Fortunately, in a first course like this one, continuity is more of a background issue. You should know what it means, you should know some of its consequences, but it's not going to be an integral part of the problems you solve on a daily basis. To motivate the discussion, think about the easiest limits there are to work. Those best limits work this way. The limit is x approaches c of f of x equals f of c. In other words, to evaluate the limit, you just plug in c to your function. Now, of course, most limits don't work this way. Usually you have to do some algebraic simplification before you plug in the c. But eventually you boil it down to a limit where you can just plug in the c. Other functions work this way right off the bat. The limit is x approaches c of sine of x equals sine of c, for instance. And that's a good thing. We're going to take this good thing and make it part of our definition of continuity. Here's the definition. We say a function f is continuous at a number x equals c if the limit is x approaches c of f of x equals f of c. There's a lot going on in this definition. There's some things to unpack. Notice that the limit is x approaches c of f of x equals f of c means that all of the following must hold. First of all, f of c has to be defined if this limit is going to equal it. Secondly, this limit has to exist. And finally, this limit that exists has to be equal to the f of c that's defined. Those two things have to be equal, as stated here. So if any one of these fails, if one or more of these conditions fail, then we say f is discontinuous at c. It's not continuous at c. So to be continuous at x equals c, each one of these properties, 1, 2, and 3, has to hold. Now let's look at some examples of this. Here's a function, y equals f of x, and an x value c. And there's a hole in the graph right here, over c. And that means that f of c is not defined. You can't plug in c into the function. So 1 fails. Now you'll see that here the limit is x approaches c of f of x. It does exist. It equals the y coordinate of this hole. So property 2 holds, although property 1 fails. And finally, property 3, we'd have to say that fails as well, because f of c is not defined, so this limit can't equal f of c. So here properties 1 and 3 fail. So here is a function that's not continuous at x equals c. For another example, in this function, f of c is defined. The limit is x approaches c of f of x exists. It equals this y coordinate. But the limit is x approaches c of f of x does not equal to f of c. So although properties 1 and 2 hold, property 3 fails. So that means this function is not continuous at the point x equals c. Here's another example. f of c is defined, so property 1 holds, but the limit as x approaches c of f of x does not exist, and also f of c can't be equal to this thing that doesn't exist, so property 3 fails. So in this case, properties 2 and 3 both fail. So this is a function that's not continuous at x equals c. And here's one where properties 1, 2, and 3 fail. The limit doesn't exist, f of c is not defined, and of course, you can't have the limit as x approaches c of f of x equals f of c if properties 1 and 2 fail. So in this case, all three properties fail. So here is a function that's not continuous at x equals c. So in every case in these drawings, we have an example of a function f that's discontinuous at x equals c. Well, what would a function look like if it is continuous at x equals c? Well, here's one. In this graph, properties 1, 2, and 3 all hold. F of c is defined. The limit as x approaches c of f of x exists, is the y-coordinate of this point. And the limit as x approaches c of f of x equals f of c. So this function is continuous at the number x equals c. Now from these pictures, you can see the geometric interpretation of continuity. A function being continuous at x equals c means that you could trace that function through the point x equals c without ever lifting your pencil. For the discontinuous functions, when you get to c, you have to lift up and put it back down and continue on. You trace the function through c, you have to lift up your pencil, go up there, come back down, and continue on like that. For a discontinuous function, there's a break in the graph of some sort at x equals c. But for a continuous function at x equals c, the function just moves right on through smoothly. So geometrically, f being continuous at x equals c means the function doesn't have a break at x equals c. Here's an example. We have a y equals f of x. And let's find the points at which f is discontinuous. Those would be the values of x for which the function has a break in the graph. And the first time you see a break as you're tracing this function is right here at x equals minus 3. You jump up. So we're discontinuous at x equals minus 3. Continuing along this function, you're in good shape. You're smoothly moving your pencil down. And then right here at x equals 1, there's a break. So we're discontinuous at x equals 1. Continuing past x equals 1, the function moves up. Right here, it looks like about at x equals 2.5, there's a hole in the graph. That's considered a break. So we're also discontinuous at x equals 2.5. So this function is discontinuous at 3 values of x, but it's continuous for all the other values of x, at least in the range of this graph. So f is continuous at any other x equals c, except for these 3. Well, why is continuity important? We'll see a couple of reasons today, but as you go through calculus, you'll see more and more reasons why continuity is very crucial. And what I can say for now is that you're going to find a lot of theorems in this course that have the following form. They'll say something to the effect of, if f is continuous, then some significant property holds. So continuity is a property that a function can have that means that you can do certain important things with that function. Now I'm being a little bit vague here. We'll flesh this in more later. But suffice to say, a function being continuous means that you can do calculus with it in some sense. So more on that later. So given that continuity is important, let's take stock of some functions that are continuous at any number c in their domains. These are the functions whose graphs are continuous unbroken curves. So first of all, polynomials and rational functions. In fact, for them, we know that the limit as x approaches c of f of x equals f of c. That's one of our limit theorems. And that's the definition of continuity at x equals c. The functions sine, cosine, tangent, cotangent, secant, and cosecant, they're all continuous at any number c in their domain. For example, we learned that the limit as x approaches c of sine of x equals sine of c. And that means this function is continuous at x equals c for any c. as long as c is in the domain of the function, meaning you can plug it in. The inverse trig functions, if you think about their graphs, they're smooth, unbroken curves, so they're continuous at any value c in their domains. A to the x, e to the x, log base b of x, ln of x, the nth root of x, they all have smooth, unbroken curves. They're continuous at any number c in their domains. So for example, ln of x is log base e of x. So since it's continuous, we know that the limit as x approaches 1 of ln of x would be what you get when you just plug 1 into x, ln of 1, or 0. Tangent inverse of x is a continuous function, so the limit as x approaches 1 of tangent inverse of x. It's just tangent inverse of 1. You just plug in the 1. And tangent inverse of 1 is pi over 4. We're going to move on now to limits of compositions. And on this slide, we're going to come up with a new limit law. As a point of departure, think about this known limit law, the one for the product. The limit as x approaches c of f of x times g of x equals the limit as x approaches c of f of x times the limit as x approaches c of g of x. This is a convenient law for working out the limit of a product, and we've used it many times. There's another way to compose two functions, to combine two functions f and g. Instead of multiplying them, you can compose them. So you might ask, is there a limit law for the limit as x approaches c of f of g of x? That's not multiplication, that's composition. And we don't have a limit law for that yet. Now the reason we don't have a limit law is that when you state the limit law for this composition, it uses continuity. I'll show you the way this works. Here's the theorem. It turns out that if the limit as x approaches c of g of x equals a number L, and in addition f is continuous at that number L, then the limit as x approaches c of f of g of x equals f of the limit as x approaches c of g of x. In other words, under these conditions, you can bring the limit as x approaches c inside the function f. This limit goes inside the function f and parks right in front of the g of x. Now for that to work, it turns out that f has to be continuous at this number, limit as x approaches c of g of x. And if f is not continuous at that number, then maybe these two things are not equal. Now don't worry about a proof of this right now. That's something that would come in a more advanced class. So just take this limit law as a fact and we'll work with it. It's certainly believable. You certainly believe that as x gets closer and closer to c, f of g of x would be f of the number that g of x is getting closer and closer to. But if you examine that really closely, you'll find that you need continuity to make it work. So this is an example of our first theorem that says basically, if f is continuous at L, then something significant happens. These two things equal. Let's look at an example. In most of the examples you use using this limit law, you don't have to worry too much about this number L, because in most examples, most problems, this outside function f, it's going to be continuous at all numbers in its domain, or maybe all real numbers. So you don't have to worry about what the limit as x approaches c of g of x is. You don't have to worry about what number L this is. You can just go straight in and bring the limit inside f. For example, the limit as z approaches 2 of sine of z squared minus 4z plus 4 all over z minus 2. This is a limit of a composition, sine of a complex function. We're taking this rational function and we're plugging it into sine. So we're composing it with sine. Now, how would we work this? Well, the outside function sine, it's like the function f here. Sine is continuous at all numbers c in its domain. So because of that, this limit law says that we can move the limit inside the sine. So we get sine of the limit as z approaches 2 of z squared minus 4z plus 4 over z minus 2. So now the problem is looking pretty familiar because we know how to work out limits that look like this. So we can work out this inside limit, keeping in mind that that number is being plugged into sine. Okay, work out this inside limit. Limit as z approaches 2 of all of this. You'll notice that you're getting a 0 on the denominator if you plug in 2. And in fact, if you plug in a 2 up here, you'll get a 0 on the top. So this limit has the form of 0 over 0. So we know we need to cancel the z minus 2 to work it out. And the top factors as z minus 2 times z minus 2. One of those z minus 2's cancel. So we get sine of the limit as z approaches 2 of z minus 2. Now this inside limit now is easy to work out because that's just the limit of a polynomial. So we just plug in 2 on the inside here. And you get sine of 2 minus 2, which is sine of 0. And that's equal to 0. So here's an example of this new limit law in action. And you should, of course, work some examples in your textbook to make sure you have a grip on this. We're moving on now to another issue that's going to be important to us, continuity on intervals. Often it'll happen that you'll have a function y equals f of x, and it may be discontinuous at a variety of points, as indicated here. But it could well happen that if you narrow your focus down to a certain interval, then that function will be continuous at every point on that interval, every number c on that interval. And in fact, if you gray out every value of x that's not on the interval for this function, on this interval, just focusing on that, there are no breaks in this graph. Initially, there was a break at b, but b is not in this interval. There was a break at a in this function because there was a hole in the graph, but a is not in the interval. So in this picture, at any number c between a and b, any number on this interval, this is a smooth, unbroken curve. So we're going to say that in a situation like this, the function f is continuous on the interval from a to b. Here's the definition of continuity on intervals. F is continuous on an open interval from a to b, like this one, if the limit as x approaches c of f of x equals f of c for any c in that interval. In other words, if f is continuous at every c in the interval. And that just means that although f may have some breaks somewhere else, it might be discontinuous somewhere else, on this interval we're safe. There are no breaks on this interval. Now, of course, not all intervals are open. You might have some closed intervals. So here's an example of a closed interval from a to b. And I've drawn here a function f of x that's discontinuous at a and it's discontinuous at b. So that looks like it's a problematic function. But look what happens when you only consider this interval from a to b, including those endpoints. I'm going to gray out everything else. As far as this interval is concerned, on this interval, there are no breaks on that graph. It looks like a smooth, unbroken curve starting at a and ending at x equals b. So that's what it means for a function f to be continuous on a closed interval. Intuitively, it just means there are no breaks on that interval, including at the endpoints, when you only restrict your attention to numbers in that interval. You don't go outside of the interval that would make you get this break here. So let's write that as a definition. You've got to be kind of careful how you express it. The definition works this way. F is continuous on a closed interval from a to b, first, if it is continuous on the open interval from a to b, so there are no breaks on that open interval. And also, the limit as x approaches a from the right of f of x equals f of a. So here we have the limit as x approaches a from the right of f of x equals f of a. In other words, there's no break in the graph as you go from x to the right of a to a. And also, the limit as x approaches b from the left of f of x has to be equal to f of b. As x approaches b, this y value f of x has to go to the y value f of b, which is right there. So these right and left-hand limits are forcing you to stay on this interval. X is approaching a from the right, and you get f of a, or x is approaching b from the left, and you get f of b. That's what it means for f to be continuous on a closed interval from a to b. So notice if there had been, instead of right here, a solid dot, that solid dot was down here, and this was an open dot, then this function would not be continuous on this closed interval from a to b, because the limit as x approaches b from the left would be this y value, but then f of b would not be equal to it. It would be down here. This is just a concise way of saying that on this closed interval, if you only look at the graph on that closed interval, there are no breaks. So for example, this function f of x, it's not continuous on the closed interval from a to b because you have a break in the graph right there at x equals b. However, look at the half open interval from a to b that's closed at a but open at b. If you gray out the rest of the graph, this curve is continuous. It has no breaks on that interval. If you delete that point b, you no longer have a break because you're not considering b. So here we have continuity on a half open or half closed interval. And it works this way. We say f is continuous on the interval from a to b that's closed at a if it's continuous on the open interval from a to b. In other words, it has no breaks on that open interval, and the limit as x approaches a from the right of f of x equals f of a. That is, x approaches a from the right, f of x has to be getting closer and closer to f of a. So you don't have a break right there at x equals a, as far as this interval is concerned. And you might also have a half open interval that's closed at the other end. We say f is continuous on the interval from a to b that's open at a and closed at b if it's continuous on the open interval from a to b and the limit as x approaches b from the left of f of x equals f of b. So I'm not going to draw a picture of that one, but you should think about it, internalize it, and read this material in the text as well. So some examples of this. Most functions that you look at, if you think about their domains, those domains are going to be intervals or unions of intervals. And it's nice to have a function that's continuous on those intervals. And that's going to work out that way most often. Think about the function f of x equals x squared minus 4 divided by x squared minus 1. If you graph this function, it's going to look something like this, as I've drawn here. This function is not defined at x equals plus or minus 1 because that gives you 0 in the denominator. And in fact, at those two values of plus or minus 1, the graph is shooting off to infinity or negative infinity. You can't plug in 0 or minus 1. The domain of this function is the interval from negative infinity to minus 1, this part. Also the interval from negative 1 to 1, this part. And the interval from 1 to infinity, this part over here. And you'll notice that on those intervals, this function is continuous. So this function is continuous on its domain, which is a union of intervals. Here's a function g of x is the square root of 1 minus x squared. And if you think about the Pythagorean theorem, you can figure out that we're talking about the upper part of the unit circle here. Its domain is the closed interval from minus 1 to 1. And this function g of x is continuous on its domain, the interval from minus 1 to 1. It's continuous on the open interval from minus 1 to 1. Also, the limit as x approaches 1 from the right of f of x equals f of minus 1. The limit as x approaches 1 from the left of g of x equals g of 1. So we get a continuous function, a function g of x that's continuous on the closed interval from minus 1 to 1. There are no breaks in this graph of g of x on that interval. So again, most functions will have intervals as their domains, and you can talk about continuity on those intervals. Sometimes we'll downplay the particular point at which a function is continuous or the set of points at which a function is continuous. And we'll just say a function is continuous if it's continuous on its domain. So for example, we'd say this is a continuous function because we really want to exclude minus 1 and 1. They're not even in the domain of the function. If you just look at the domain of this function, it's continuous on these intervals. So you might say this is a continuous function. It doesn't have any breaks in its graph as long as you stay in its domain. It's important to know that functions you're dealing with are continuous, and you can actually build them up from basic continuous functions. I'll give you a list of our basic continuous functions, and by this I mean they're continuous on their domains. Constant functions k, x to the power of n, e to the power of x, b to the power of x, ln of x, log base b of x. They're all continuous on their domains. Because your experience with these functions tells you that their graphs are continuous unbroken curves. Also, the 6 trigonometric functions, their inverses, all have smooth, unbroken curves, so they're continuous on their domains. Functions like the absolute value of x could be added to this list. Now, you can combine functions, f of x, that are continuous on their domains and get other continuous functions. For example, think about this limit law for the product. And let's say that f and g are both continuous on their domains, and both continuous at c, let's say. Look at the limit as x approaches c of f of x times g of x. We have a limit law that says that's the limit as x approaches c of f of x times the limit as x approaches c of g of x. And because f and c are continuous at c, the first limit equals f of c, and the second limit equals g of c. So we see here that the limit as x approaches c of f of x times g of x equals f of c times g of c. In other words, to work out the limit of the product, just plug in c into the product. And that's saying that the function f of x times g of x is continuous at c. In fact, it's continuous at any number c that's in the domain of the product. And you can do this for any limit law. This limit law is telling us that the product of two continuous functions is continuous. We also have a limit law for the sum of two functions, and if those two functions are continuous, you get a corresponding fact that the sum of those two functions are continuous, using the limit law as we did here. So I'll put a box here titled Building Continuous Functions to carry our discussion to its natural conclusion. If f and g are continuous on their domains, then so are the following. F of x times g of x, for the reason we stated here. Also f of x plus g of x, because you could use the corresponding limit law for f of x plus g of x, you'd get f of c plus g of c. And you'd conclude that f of x plus g of x is continuous at any number c in its domain. F of x minus g of x is going to be continuous. A constant k times f of x divided by g of x, using the limit law for the quotient. F of g of x, the composition, using the limit law that we discussed earlier today. F of x to the power of n, absolute value of f of x, and the nth root of f of x. All of those are going to be continuous on their domains, and you can show that using limit laws as we did in this specific example. So this tells us that we can take continuous functions f and g and combine them using the operation stated here and be guaranteed that we're going to get a continuous function. A function that's continuous on whatever its domain is. So you can take these basic continuous functions and combine them with operations that we've listed here, and you're guaranteed that what you're going to get is going to be a continuous function. So as an example, think about the function h of x equals cosine of x plus x squared divided by sine x plus 5 squared root of x. You can conclude from what we said here that this is continuous on whatever its domain is. Why? Because look, it's built up out of continuous functions. Cosine of x was one of our basic continuous functions, plus x squared. That was a basic continuous function. So cosine x plus x squared is continuous. Sine of x is continuous. The quotient of those two is guaranteed to be continuous. Then you're adding on a 5 times square root of x. The 5 times the square root of x, that's a constant times square root of x, a continuous function. So the product of those two continuous functions is going to be continuous. And now you're adding two continuous functions together, and you're guaranteed to get a continuous function. So any complex function like this h of x, that you've built up out of basic continuous functions using these operations, that's guaranteed to be continuous. Now, for the most part, you're not going to be thinking about this in the exact way that we thought about it here. You're just going to be working with functions, and in the background, you're going to know that they're continuous. It's going to become second nature to you. It's not part of your active mathematical reasoning as you're working calculus. Basically, this building up of continuous functions sort of gives us license to work with the usual kinds of functions we work with in calculus on a daily basis. And in the background, just know that they're continuous, and to know that we can apply various theorems to them that demand continuity. One of those theorems is what's called the intermediate value theorem. And I want to spend some time talking about this. I'm going to state this theorem sentence by sentence. It's a theorem that it's good to have in your toolbox. It's not going to be the most important theorem in calculus, but it uses continuity, and it's something that every once in a while you'll need to trot out and use. It works like this. Here's what it says. It starts out, if f of x is continuous on a closed interval from a to b, and off to the side I've drawn this closed interval from a to b with a continuous function on it, and y naught is any number between f of a and f of b. So here's a y naught that's between f of a and f of b. Then the theorem asserts there is a number c in the closed interval from a to b for which f of c equals y naught. So it's saying that under these circumstances, given this continuous function, you pick a y value between f of a and f of b, you're guaranteed to be able to find some number c in the closed interval from a to b for which f of c equals y naught. If f of x is continuous on a closed interval from a to b, and y naught is any number between f of a and f of b, then there is a number c in the closed interval for which f of c equals y naught. That's the intermediate value theorem. You can paraphrase this as saying a continuous function on a closed interval starting at height f of a and ending at height f of b attains every height y naught between f of a and f of b. In other words, no matter what y naught you pick between f of a and f of b, you're going to be able to find a number c where f of c equals that y naught. That's what the intermediate value theorem says. Now, you would certainly believe this theorem. It's very intuitive. Just drawing pictures of functions that are continuous, they have no breaks in them. You'll convince yourself that it certainly has to be true. And actually, to prove this theorem rigorously, it's rather complex. It's the kind of thing that you would tackle in an advanced calculus class. There are a number of subtleties that pop up when you examine this closely. But for us in this class, we'll just take the intermediate value theorem as a very intuitive and plausible theorem. It's actually true, and we have license to use it. As an application, we're going to solve this example. Show that the equation 2 to the x minus x equals 4 has a solution. Now, if you look at this equation and you try to solve for x, you're going to run into some problems because it's impossible to isolate x. X is an exponent and is also not an exponent. It occurs twice. And if you try to bring this exponent down by taking isolating the 2 to the x and taking a log, then suddenly you'll have a log of a term involving x on the other side, so then x is trapped inside the log. You're just not going to be able to isolate x. So you can't solve this equation with traditional means. Yet what we propose to do in this example is to show that it does have a solution. We're not going to find the solution, we just want to show that it has a solution, which could be the first step in finding the solution. Here's our strategy. Let's let f of x be the function 2 to the x minus x. So the question becomes whether f of x equals 4 has a solution. Since f of x now is 2 to the x minus x, f of x equals 4 is the same equation that we had up here. So does f of x equal 4 have a solution? Can you find a number c such that f of c equals 4? That's what we're asking. To solve this problem, we're going to set it up so we can apply the intermediate value theorem. Let's first of all pick a number, and I'm picking this number kind of at random. Let's just take 1, it's a convenient number, and think about that as like your a. F of 1 is 2 to the 1 minus 1, and it equals 1. So f of 1 equals 1. Now what we're going to try to do here is to find another value of x so that f of x equals a number that's bigger than 4. So then 4 will be between 1, or f of a, and f of b, and will be guaranteed a number c such that f of c equals 4 by the intermediate value theorem. Let's see if we can carry out that plan. Think about f of 3. It's 2 cubed minus 3 equals 5. Ah, that's good, because now f of 3 equals 5, and 4 lines between 1 and 5. It can be our why not. So 4 is between f of 1 and f of 3. It's right there. Also, f is continuous on the closed interval from 1 to 3 because f is built up as a difference of two continuous functions, 2 to the x and x, that are continuous on this closed interval. And there it is. There's the graph of y equals f of x. It looks something like that. So the intermediate value theorem applies here, and it says that there is a number c in this closed interval for which f of c equals 4. And it looks like that c is about right here. F of c equals 4. So we're guaranteed to have such a number c. Plug it into f, you get 4. But f of x is the function 2 to the x minus x, so f of c is 2 to the c minus c. So we have a number c for which 2 to the c minus c equals 4. And that means the equation 2 to the x minus x equals 4 has a solution, namely this number c. And that completes our solution. So this has been one application of the intermediate value theorem. You can use it to show that solutions of certain equations exist. That's it for today. We've talked about continuity and some of its consequences. Next time, in Lecture 12, we're going to look at limits that have the form of the limit as x approaches c of f of x equals not a number, not a finite number, but infinity. Those are called infinite limits. And then, in Lecture 13, we will investigate limits that look like the limit as x approaches infinity of f of x equals a number L. And that'll be it for part 2. Then in Lecture 14, we're on to part 3, the real substance of this course, derivatives. So it's coming up, it's on the horizon. And I'll see you next time. Goodbye.